All right, in this last topic of the course, we're going to talk about nuclear energy. All right, pretty momentous occasion for us. This is the last thing that we talk about in regular physics, and it's a really interesting topic. It's an important topic politically, environmentally, and the thing about nuclear energy is we got to understand what goes on in the atom first. And we've talked about the atom before in this class, most specifically when we talked about electricity. And electricity is called electricity because it only involves the electrons theoretically whirling around the outside, around the nucleus, around the outside of the atom. But what's interesting is that every chemical reaction that you've talked about most chemical reactions that you've talked about in chemistry, most chemical reactions that we observe on a day-to-day basis, electricity, all the things we've talked about involve only electrons, right? The neutrons and protons really don't play that much of a role. At least they don't transfer from one place to another. And the interesting thing about that is that all those things involve only about 0.01% of all of the mass that we're talking about in the atom. Inside the nucleus, we have about 99.9% of the mass of the atom. So it's interesting that most of the things that happen on a day-to-day basis just involve the stuff that's going on out here. This influences everything because this influences what goes on here, but it's the electrons that play the role in transferring from one place to another and participating in chemical reactions. So when we get down inside the nucleus, we're working with a ton more mass, lots more mass than we've been working with before. For that reason, nuclear energy is extremely great. We can get a lot of energy out of the nucleus. Now, as we talk about the nucleus, let's draw this again. We got our electrons out here, we know that. And what's interesting, let's blow this up a little bit actually. What's interesting about the nucleus is, as we know, there are protons in the nucleus and there are neutrons in the nucleus. Just draw 3 just for the heck of it. Oh, let's draw 4. Let's make 4 of them. So there's all these protons and neutrons. We understand that the protons are positively charged and the neutrons are neutral. There are some interesting interactions that go on in the nucleus because just from what we've talked about so far in this course, just with static electricity, just with electrostatic forces, the way that we draw the nucleus now, there's a problem with it because these are two positives. They participate in the electrostatic force. The neutrons, however, do not participate in the electrostatic force. And so what's interesting is two positives, as we know, they repel each other. And the electrostatic force, as we also know, if we have these two protons, as we begin to bring them closer together, now this doesn't mean that they attract each other, but as they come closer together, we know that the electrostatic force increases. And so the interesting thing about that is that this nucleus is extremely dense. The electron portion of the atom is this large cloud that's extremely or not dense at all. The point is these protons are tightly packed. They're very close together. And it doesn't make sense at first because protons are supposed to repel each other, especially when they're close to each other. So we know that there's a repulsive force between all the protons in this nucleus. This proton wants to go away from this one. This proton wants to go away from this one. You understand the point. There's a big repulsive force that wants to blow this nucleus apart because of the repulsive force with the protons. So at first glance, the nucleus doesn't make sense because it's not supposed to stay together. But on a daily basis, we don't observe that the nucleus blows apart. For the most part, in most normal everyday situations, the nucleus stays together. One atom remains the same type of atom. And so scientists begin to postulate what must be causing this, because we know if there's a force that's pulling outward on the nucleus and we observe that that nucleus doesn't blow apart, then that means there must be another force pulling inward trying to keep the nucleus together. And they knew that that force must be inside the nucleus. We knew that the force must be strong because it takes a lot of force to break it apart. And so we called it the strong nuclear force, right? Really, STR, strong, not storm, strong nuclear force. That's the force that's holding the nucleus together. The strong nuclear force is interesting for a few reasons. It's postulated or hypothesized that strong nuclear force only acts within short distances, like within the nucleus. If we get these particles outside of the nucleus that far apart, the strong nuclear force doesn't work anymore. And the strong nuclear force only acts between particles in the nucleus. And collectively, we call all these particles in the nucleus nucleons. A nucleon is either a proton or a neutron. So strong nuclear force only acts between nucleons. So it's interesting that, so there's a strong nuclear force between neutrons and neutrons. There's a strong nuclear force between protons and neutrons. And there's also, interestingly enough, a strong nuclear force between protons and protons. So you have these two protons that are repelling each other with the electrostatic force, and at the same time they're attracting each other with the strong nuclear force. It's kind of two different forces in opposite directions. So we've got these two forces going on inside the nucleus. We have the electrostatic force as well as the strong nuclear force. Strong nuclear force is the strongest force that we've talked about so far in this course. It's much stronger than the electrostatic force. That's why we observe the nucleus to hold together. So two things to take away from this. Number one is that 99.9% of the mass is contained in the nucleus. We're going to see in a minute that mass can be converted to energy. And because there's so much mass in the nucleus, there's a lot of energy stored up in the nucleus. And this mass, combined with the strong nuclear force keeping it together, gives us that amount of energy. And the strong nuclear force, I equate to, let's just imagine that you were, trying to open a drawer on a desk, and that drawer is stuck. You're pulling on it with a lot of force. When that thing finally comes loose, it's dangerous because you could go flying. And that's kind of the same concept with here. This strong nuclear force is so strong, and there's so much mass here in the nucleus, that when this thing finally comes loose, there are special things that we can do to make the nuclear force kind of let go. When that thing lets go, we get a lot of energy out of it. This strong force is converted into quite a bit of energy, and it's kind of the same concept here. So a lot of mass in the nucleus combined with a strong nuclear force means that we get lots and lots of mass or energy out of the nucleus. That's why we call it nuclear energy. The other thing that we need to consider is that the strong nuclear force is interesting because it operates between all of these particles. But if it's between a proton and a proton, that force is counteracted by the electrostatic force. However, since the neutrons don't participate in the electrostatic force, the neutrons kind of become the sort of glue for the nucleus, if you will. And so the presence of the neutrons, because neutrons hold themselves together and they hold themselves to the protons, the more neutrons there are, the tighter this nucleus holds together, right? And the more protons there are, the more this nucleus wants to blow apart. So there's a delicate balance between protons and neutrons. And the more massive this thing gets, that ratio will change a little bit. But the point is that if we mess with that balance of protons and neutrons with something such as an isotope, remember an isotope from chemistry is something that it's the same element that simply has more neutrons. We add neutrons to the element. It doesn't change the reactivity of the element, such as we can have uranium-235, and then the other isotope, the most common isotope of uranium, is uranium-238. It's got 3 more neutrons in it. It doesn't change the chemical properties of it, but it does change the mass, and it changes the fact that when you put more neutrons in here, it does make the nucleus hold together tighter, but it also makes the nucleus unstable, and the nucleus doesn't want to be unstable. So the nucleus can go through a process called decay to try to make itself stable again, and we'll talk about decay processes in a little bit. But this is the basics behind nuclear energy. You need to understand this concept of what goes on in the nucleus. There's an electrostatic force trying to pull the nucleus apart. There's a strong nuclear force counteracting that force that wants to keep the nucleus together. And so because of the mass and the strong nuclear force, we get tons of energy out of the nucleus, potentially, in the right situations. And because of the interaction of these forces, there's a delicate balance between protons and neutrons in the nucleus with each element. If we throw off that balance, For instance, with an isotope, we get radioactivity, we get decay, and we could possibly get very strong nuclear reactions. Now, actually, what I advise you to do at this point is go in here to my website, click on teaching videos, and go down here to atomic and nuclear physics. And there's a video in there from Veritasium. You'll see nuclear meltdowns, chain reaction videos. This one right here from Veritasium calls Where Does the Sun Get Its Energy? I would pause the video right now and watch that one if I were you, because in that video Derek talks about this mass energy equivalence thing, and I'm gonna explain it to you right now, but in explaining it I'm going to assume that you've kind of watched this video and know what he's talking about. So go ahead and pause the video now, go and watch this one from my website, and then come back to what we're going to talk about right now.